So now we have Jules Jacobs from Cornell. We will have another paper that's not from Cornell later in the program, but don't worry. But I understand now big red cats after the first speaker, so thank you. So please carry on talking about still, I guess, the similar issue as the previous talk.
Yep, that's right. Yeah, I'm going to talk about StacKAT, which is similar to NetKAT, is an extension of NetKAT. And this is joint work with Nate and Jana, who are here, and with Tobias, Dexter, and Lily, who are not here, I think. And if you want to play along, you can use this URL. So what is StacKAT about? Well, let me first tell you about the network model that we are talking about. So Mark already talked about that a bit. But here you see a network and a packet traveling in a network. And what is a packet? Well, a packet is just a fixed collection of header fields. Here on the bottom you see that it has a source address, it has a TTL, some other fields. And we also consider the current location of the switch to be part of the packet, but it's not a real field that's stored in actual bits of the packet, just for us to keep track of where the packet is in the network, and to uniformly treat the location with the actual data. So in this model, a switch looks at these header fields, modifies them in some way, and sends the packet out to a neighbor. And that's all a switch does. So a switch is a very simple finite state thing here. And then NetKAT is a language to model these kind of networks using PL techniques. So what is the idea? The idea is to write a simple imperative program for the behavior of your network, where the local variables correspond to the header fields in the packet. So here you see you have an input packet here, and a simple program that transforms this packet, produces an output packet in its local variables. And this way, we can model many things that switches do. For example, a match rule in a switch can be modeled using an if statement. An action can be modeled using a variable update. Multi-hops can be modeled using loops. And then verification can use techniques for program verification. And in particular, since programs are very simple here, we can do automated verification because everything is decidable. And the key verification question that's answered here is whether two programs are equivalent. And many network verification questions can be reduced to that question about programs. Okay, so why are we doing things beyond NetKAT? Well, the thing with NetKAT is it can only model packets with a fixed number of fields. And each of these fields also must have a fixed number of bits. So that means that you cannot model variable length data. You cannot model packet parsing. You cannot model certain protocols that use arbitrary amounts of data in the packet, such as source routing, where the entire path that the packet is supposed to take is stored in the packet payload. It can also not handle tunneling, where a packet is encapsulated, because that also extends the size of the packet. So this paper is about addressing this limitation and going beyond this finite state model to an infinite state model. So that is what StacKAT is. So the only thing we do is we model an extra field in the packet, the last field, which contains a payload which is variable size. And the key thing here is that this extra field is treated as a stack. So we can push new bits onto it or pop bits off from it. So as I said, we know from NetKAT that we can reduce network verification questions to program equivalence. So what we want to build here is a model for this variable state packets where we still have decidable equivalence. So here's an animation of what these kind of networks look like. So everything is the same as before, but you see here the last field, the payload, is being modified and some bits are being pushed onto it or popped off. And those bits can, of course, be stored in header fields. It's just an arbitrary program, but it can only treat the payload as a stack. So here's what the actual language looks like. It's more or less like regular expressions. Here, the first line in the grammar is just your ordinary regular expression constructs, plus the two constructs for NetKAT for assigning a packet field and testing a packet field. And then we have two additional constructs for pushing and popping onto the stack. And with these two operations, we can model this extra field, which lets us model all these extra protocols. So let's see what the stack operations do. Well, push is very familiar. It just takes an input stack, puts the new number in front. pop is a little strange because you see pop here also has a constant argument. That's maybe unexpected. So pop here acts as a non-deterministic operation that either succeeds or fails. So if the stack's current top is the actual number, then it pops it off. Otherwise, it non-deterministically fails. So here you see in the bottom, if the top of the stack doesn't match, it fails, so the program behavior is the empty set. And if the stack was empty, it also fails. Okay, so we have this language with regular expressions, but actually this is just a core language in which many familiar constructs can be modeled. For example, an if-then-else statement can be modeled as a non-deterministic choice, where you either test that some field is, for example, 0, and then do p, or you test that some field is 1, and then do q. You can also encode while loops using clean algebra star, where you say, okay, while the field is 0, keep repeating this, and then at the end of the loop, field must be 1. Using these concepts, we can also model interaction between header fields and stack. For example, here, push of a Boolean field f can be modeled as first testing if the field is 0, then pushing 0, or testing that the field is 1 and pushing 1. Similarly, pop can be modeled the same way. Since pop acts as a test, we can test if the top of the stack is 0, pop it off, put it in a field, and do the same with 1. Note that this can be expanded into n-ary length for fields that can store more values. So what is the semantics of all this? Well, the semantics is simply a familiar small step semantics, where the input state is an input packet with fields and a stack, and the semantics of the expression then steps this to a set of output packets, all with a stack. And then if the set of output packets is empty, the packet is dropped. If there is one packet in the output set, it's just a deterministic step. There can also be non-deterministic steps for modeling multicast, for example. And the denotational semantics of this is very nice and simple. So sequential composition in the language is just relational composition. Non-deterministic choice is just union of relations. Clean star is just reflexive transitive closure of the relations. And then the basic operations, they have the usual semantics that you would think of. So what is the key verification question? That is the semantics of one expression equal to another? So in NetKAT, it is somehow clear that this question is decidable because everything is finite state. So you can just enumerate the entire packet space and compare automata. And this is p-space complete because comparing NFAs is p-space complete. But for StacKAT, this is not very clear because we have this unbounded state space. And so it's not very clear that this question is even decidable. But it turns out that it is, and in this case, it becomes X-space complete. So in the rest of the talk, I want to give you some intuition for the difficulty of this question and then how this is solved. So here I list 3 basic StacKAT equivalences. So the top one says if you first push a value and then pop a value, this is equal to doing nothing, just the identity. So if you push a value and then try to pop off a different value, then this is a failing program. It's the same as just deterministically failing. And then the last equivalence is maybe a bit more interesting. So if you pop a value v and then push it back, this is almost the identity, but not quite, because if the input stack didn't start with v, it would fail. But if you add in the identity on the left, then it does become the identity. Okay, so here's maybe a more interesting equivalence. So here you see on the left, you can push any number of a's, and then pop any number of a's. Turns out this is the same as either pushing a number of a's and then popping a number of a's. So why is this? Because if you push some number of a's and then pop some number of a's, the net effect is always to either having pushed some or popped some, depending on whether you did more pushes or more pops. So here you can do a puzzle and see which ones are equivalent here. But I hope this works. But we have a tool for this. So now I do need to move my mouse on this screen. So here you see 2 expressions. On the left, we say we pop any number of 1s and then push a 1. On the right, we push a 1 and then push any number of 1s and then pop a 1. Turns out that these expressions are not equivalent. and our tool can tell you why. So here it gives a counterexample both ways for a transformation that can be done by the left but not the right, and vice versa. And I think I can type here. So we could also, for example, put a star here, and now it does become greater than the other side. And if we put another star on the right, you see that these programs are equivalent. Popping some number once and then pushing one is the same as pushing once and then popping once. Okay. All right, so how does this tool work? So it works in 3 steps, basically. The first step is, the 0th step is to take your program and convert it to an NFA. So this is, you're all familiar with this. But because of the header fields, it is a little bit more involved. I will go into that in the next slide. And then we do 3 normalization steps on the automaton. And at the end of the day, it will be true that if 2 programs were semantically equivalent in the denotation of semantics, then the automata will be language equivalent, so they will accept the same words. But that's only true in after step 3. So let me go into step 0. How does that work? So in step 0, we use small step semantics, where we only take into account operations on the headers, and we keep the operations on the stack as labels on the transitions. So that means that the state in this small step semantics only stores 2 things. One, the state of the header fields, 2, the current expression that we are executing. And it turns out that if you step this way, you only reach finally many states. So you get a finite automaton generated by the operational semantics. And on the edges of the automaton are the push and pop operations that you do. So now we have an NFA, maybe a large NFA, where the labels on the edges are push or pop, or epsilon. So then the next step that we do is we try to cancel out matching push and pop operations. So if somewhere in the automaton we see push v, and then the next step will be pop v, we can insert an epsilon edge to shortcut this. So instead of actually doing the push and the pop, we could instead just directly go to the resulting state. And formally to do this, we have the rule above where we insist that there is an epsilon edge between the push and the pop. And separately we maintain that we maintain the reflexive transitive closure of the epsilon edges. So this way, by exhaustively applying these rules, it stabilizes because we're only adding epsilon edges to the automaton. So eventually nothing more gets added, and then we have step 1. Then after step 1, we will intersect the automaton with the language pop star, push star. So that means that we throw away all the strings in the automaton that have a push coming before a pop. We only keep the ones that have pops before pushes. So intuitively what this does is it removes inconsistent push-pop operations, and it also actually removes consistent push-pop operations. And the reason that's okay is because we did it step 1, where we inserted a shortcut edge for them. So now we have an automaton that is even more canonicalized. But it turns out it's not quite enough. It's still not true that 2 automata are language equivalent if the expressions were semantically equivalent. So for that we need step 3, which is a bit more complicated. And basically the idea here is to start running the automaton from the inside out. So we start at a position in the automaton where on the left we have a pop operation and on the right we have a push operation. Note that after the previous step all strings are of that form. They have some middle part where we go from pops to pushes. So we look at that point and we execute the automaton from the middle out in synchronized pair steps. So now instead of having 1 operation on the label, we have 2 operations, a pop on the left and a push on the right. And if we are at the end on the left, we have a special done marker, the same on the right. So now that we have the automaton in this shape, we can add self loops to the start state, intuitively representing which part of the stack was not touched by the program. So initially, the stack would have some number of values on it. And these self loops represent those parts that are not touched by the program. After we have done this step, it turns out that indeed, 2 expressions are language equivalent, even only if they are semantically equivalent. So a common question that comes up is, isn't it just visibly pushdown languages? It turns out, no, this is quite different, because in visibly pushdown languages you have restricted stack behavior, namely visibly pushdown behavior. So in StacKAT, there is no restriction on the stack behavior. Any push or pop is allowed at any point. On the other hand, in visibly pushdown language, you have a separate input tape, but in StacKAT there's no input tape, there's only the stack. So the input in StacKAT is sort of what is stored on the stack before you start running your program. So that is the initial packet that comes in. So the initial packet is not on a separate tape, but it's on the same stack. In fact, if you were to add an extra input tape to StacKAT, it would make the whole equivalence undecidable. So we can't do that. Okay, so what about the difficulty of solving this problem? It turns out that if you don't have any header fields, this problem is equivalence problem is p-space complete. If you have header fields, it becomes x-space complete. And one of our previous reviewers gave an idea for a very elegant reduction here from regexes with squaring. So if you look at the actual performance of our tool, there are sort of two regimes. One regime is without header fields. Those are the lines at the bottom. And then it goes reasonably fast. If you do add header fields, it becomes very slow. So one future direction here is to treat the header field symbolically, like was done in previous work, and try to speed this up. But how to do it is not super clear. So then another thing that's in the paper is a complete axiomatization. So on the left here we have the three axioms that we saw in the beginning. It turns out that we were not able to prove that these axioms are complete, meaning that if two expressions are equivalent, then you can prove that using these axioms. So instead we replaced the third axiom with an ugly axiom, which you can find in the paper. And now we are able to prove it. So challenge to you is to prove it for the left set of axioms. So what I talked about is a new model for unbounded packet processing with decidable equivalence. And to make this actually work for real-world networks, we would need a more familiar surface syntax, a symbolic algorithm to treat the packet space, the header space symbolically. And ideally, we have completeness proof for the nice axioms. That's it. Thank you very much.
All right. Does anyone have any questions? Oh, well, Umang, if you can come up because of the recording. Oh, you Bill, I mean, you go first too. Thanks. Yeah.
Hi, Chris Casmangino, Jane Street. As a non-expert on automata, your algorithm with the 3 steps basically looked like black magic to me. Are these steps like standard in this literature, or did you just come up with these out of thin air, or I don't know?
Yeah, out of thin air, yeah.
Thanks.
Great talk. I'm Umang Mathur at NUS, and I have a similar question. I acknowledge that it is black magic, but I'd like to sort of untangle some of the magic. Is there a more declarative understanding of what this operational procedure is doing? Like, okay, here is a language, step 1 is XYZ closure of that language, and then step 2 is this other kind of closure. Is there a...
So it is a bit difficult because so the problem here is that step 2 only makes sense if you have done step 1. So step 2 doesn't make sense on any regular language. It only makes sense on the languages coming out of step 1. So that's one difficulty. Another difficulty is that step 2 to 3 is changing the alphabet of the language totally to this paired alphabet. So that also doesn't match the traditional ways of doing reductions in clean algebra. So
yeah. So I don't think clean algebra will have an answer to what I'm looking for. I'm looking for an answer which is language theoretic or automata theoretic. So for example, could it be that maybe step 2 is some homomorphic image of step 1, that sort of thing? That step 2 is really a homomorphism of the output of on top of the output of step 1. Is there something like that?
So the way the correctness proof works in the paper is just reasoning about the operational behavior of the program. So it would be interesting to see if we can make that nicer using something like this, but we haven't done so. We just grind through the proof manually.
Okay, thank you.
Thank you very much.